Welcome to the presentation of our paper Deep Compliant Control for Legged Robots. In this work, we present a deep reinforcement learning approach to create a motion controller that uses compliant behaviors in the presence of external disturbances. We explore the impact of such compliant motions in the sense of robustness and energy efficiency. This controller was trained purely in simulation and successfully transferred to a robot in the real world. Taking a glance at nature, we can see the stability of animal locomotion under external disturbances. Even under heavy external influence, like this dog owner here in the video, its motion is stable and adapts to the force applied to it. Here we see that animals instinctively adapt to external influences and change their motions accordingly. This kind of compliance is what we are trying to reproduce through deep reinforcement learning. Now to the setup. We use the traditional agent environment loop with an agent trained with proximal policy optimization. It outputs 12 joint angles for the robot. Feeding this through the environment, with the robot we generate the observation. Our observation contains a reduced state that describes its local pose and motion. Additionally, since we want the agent to estimate external disturbances, we want it to be able to estimate forces. Through the low-level PD controllers in the joints, torques are related to the action with its corresponding state observation. By passing the most recent action together with the last observation to the agent, we give it all information to estimate the external force acting on it. For our reward, we use a common structure of rewarding and penalizing. We reward the agent for following the given command, as well as taking large steps to generate a visually pleasing walking motion. Further, we penalize for energy consumption, motor torques, and weird body poses. With this setup, we can now introduce our multi-stage episodic reinforcement learning training. We divide the training episode into 3 distinct stages: walking, recovery, and post-recovery. We do this to emphasize that objectives change depending on environmental context, such as being pushed or walking on uneven ground. The first stage is the walking stage. Here we start by sampling a random command, such as linear speed for forward and sideways walking, as well as rotational speed for turning. In this stage, we let the agent simply follow the motion command without any disturbances. Also, it receives the unchanged reward as introduced before. Before we enter the next stage, we apply a push to the robot by offsetting its base velocity by a random amount. This leads us to the recovery stage. Here, the goal is to recover in a compliant way. To achieve this, we give the agent a time frame of 1 second, where it does not get any punishment for bad command tracking. We want to shift the priority from accurate tracking to an efficient recovery. So here we adapt our reward structure and replace the tracking reward with a constant value. When the agent has recovered from the push, it needs to walk again according to the command. So in the third stage, we switch back to the default reward to maintain a proper walking. Here we simply want to avoid a degrading of walking after disturbance. With this trained policy, we can now make some analysis. For this, we always use 2 different policies. One is the compliant policy, as we trained with the multi-stage procedure. The competitor is a baseline that was trained without the multi-stage training and used the same unchanged reward even during disturbances. To get a proper measure of the compliance, we let the robot walk, and when applying a push, we measured the time it took to recover. On the left side, we applied the push while the robot was standing still. On the right side, it was walking forward at maximum speed. In both scenarios, we see that our compliant policy takes significantly more time to recover from the push, which shows a more compliant behavior. Like we have intended with our multi-stage training, by taking more time for the recovery, the compliant policy puts more priority on energy efficiency, As a result, it uses around 15% less energy after being pushed, compared to the baseline. Also, the motor torques improved slightly by 6%. Apart from simple compliance, we also gained a very robust policy that can navigate through obstacles it has never seen before. Also, it does better than the baseline, which seems a little overwhelmed by the presented ball pit. Another aspect of compliant motion is the force applied onto the environment in case of collisions. For this experiment, we placed a large box inside the simulation and let the robot collide with it. We see that the baseline applied much more force into the box and displaced it further than the compliant one. Here we can argue that the policy provides more safety in collaboration with humans or inside of fragile environments. Finally, we did not only put this policy to work in the simulation, but also ran it on the Unitree Go 1 robot. For a real-world comparison, we mounted a pulley with a weight to the robot to apply a constant force. Note that here the robot always received the command to stand still. We see how the baseline mostly struggles with resisting to the force, while the compliant one walks smoothly with the force. And to show its overall robustness, we took a robot for a walk in the park. Thank you very much for listening.